Hi, my name is Caio and I'm a third-year mechanical engineering student from Brazil, currently spending one semester here in New York University. In EECS3612, I was able to learn the way sensors work and how to analyze its circuits. As I study mechanical engineering, my project for this course was a little bit different from the others. My goal was to analyze the behavior of a fluid inside a microfluidic device. These devices are made of micrometer-sized channels where a fluid flows. They are widely used in biological, chemical, and medical applications. The design made for this project was meant to be for cell culture applications. In this video, I'm going to show how to simulate a fluid flow using the software ANSYS AIM Student. ANSYS has a bunch of templates that really make life easier. As we want to simulate a fluid flow, we can choose the template from the software menu. Then, it's going to ask whether we want to create a new geometry or import a geometry file. I already have a 3D model that was previously made inside the software Rhino, so I'm going to choose the second option. Next step is to choose which additional parameters we want to have. For this simulation, I'm going to leave as it is. Now, we click the tab Geometry. First, I'm going to rotate the object so it has the right orientation. It is possible to rotate it 90 degrees by double-clicking the arrow or typing a value for the angle. In order to prepare the model for the simulation, we need to extract the flow volume. This can be done by clicking on the volume extract and then selecting the face that surrounds the region we want. Then, to determine the inside of the region, we need to select a seed face. Now, we just need to click the check button and close the Geometry tab. We can hide the body so we see our flow volume only. Next step is to create a mesh. We can go to the Mesh section by clicking the button on the bottom. It is necessary to define our boundary layer, that is, the walls that surround our flow volume. Then, we can go back and click on Generate Mesh. As you can see, now our mesh is ready. Next step is to go to Physics tab. Here we have a bunch of menus. By going to Physics region, we can choose if you want to solve the simulation not only for fluid, but for thermal effects as well. We need to tell ANSYS what is our physical region. We can do that by using the body selection tool, selecting the whole body and then clicking the button. Under Material Assignments, we can select which material we're going to have in our simulation. In this case, I'm going to choose water. We can also select the physical state and the material distribution. We can check the parameters used for the material we select as well. Now, we need to set the initial conditions. We can do this by selecting the first face and double-clicking on it. Then, we click on Add, Fluid Flow Conditions and Inlet. We can select between pressure, velocity, and mass flow for the parameter. I'm going to leave as velocity. Now we type the value we want for it and select the unit. We do the same thing for the outlet, but for the parameter, I'm going to choose pressure and set it as 1 atm, that is, 1 atmosphere. Finally, we can set the other faces as walls by right-clicking on the screen and choosing Wall. We can change the options here as well, but it's good for the simulation already. Now, we can click on Solve and wait for our simulation to finish. Once it's done, we can go to the Results tab, select which variable we want to measure and click Evaluate. We can also change the symbol distribution, so we can see the results better. The software also gives us the calculated maximum and minimum, as well as the average. The simulation was run 3 times for 2 types of designs, one with smooth curves and the other one with sharp edges. When comparing both, it was possible to see that the smooth curves helped to raise the velocity of the fluid flow. When the speed on the inlet was changed, all the other parameters changed as well. When it was double, the viscous force, the velocity on the channel, and the shear stress were also double. That allows us to see that these parameters follow a linear relation with the input velocity. When the simulations were compared to calculations made by hand, it was possible to see that the simulations make sense. But it's easier to think that the simulations are more precise, because for the calculations made by hand, we need to make some assumptions and some simplifications.